Okay, so thank you to all the students who made it here on Saturday. And of course, thank you to all the student organizers for running this workshop pretty smoothly, all the travel arrangements and everything else. So I think, kudos to you. It's a good thing to present later on in the workshop because then I can leverage some of the concepts that already has been presented over here. So, so I don't have to go over those things. So before I, because I think I will probably run out of time, so I will acknowledge everyone in my lab who has supported all this research, past and current students. But the work that I'm going to talk about is funded by NSF. Okay. So just to say, in my lab, the research focus is mainly analog. And I think Jennifer, in her earlier talk, said, okay, where is the analog advantage? Analog advantage generally shows up when you're exploiting the physics of the device to do computing. And generally, those show up in two extremes. One, at the edge, where you have to deal with analog signals, because real world, the signals that you acquire is analog. And on the high end, where the frequencies or the rates are so high that digital also becomes analog. So it's better to use some of those analog computing techniques. So my group focuses on those two extremes. I will show one example of a project that has been going on for several years, and then we kind of moved away from this. So this is actually, I would say, a tactile sensor, but for large structures like bridges. So here you can think of, these are piezoelectric fingers. And the idea here is that the piezoelectricity automatically generates enough energy. And if you are able to exploit the physics of that energy generation to drive the synapses, which are there on this chip, so they are, yes, Jennifer, they are floating gates, and they work very well. To drive the physics of the floating gates, then you can do storage and some computation, some feature extraction right at the edge. Okay? So initially, our grand vision was, and this is where, when Rajit, when he presented, he talked about Amdahl's law. So here I will also show the effect of Amdahl's law. We originally thought that we will make everything self-powered, harvesting the energy from the environment. But it turns out that you have to communicate the data too. And for communication, especially for practical environments, in this case it's a bridge, you have to transmit data over a kilometer. So you have to put some battery, some energy storage in it. And so then from self-powered, it became quasi-self-powered. Okay? But some of the primitives still were there. Because we were doing feature extraction at such a low energy footprint, the number of wireless transmissions that you have to do went down significantly. And especially if you have to do this over this bridge. So this is where we had our deployment study. This is a Mackinac Bridge in the Great Lakes. It's about 5 miles long, span to span. So from here, so folks who are local, from here to Indiranagar. And imagine you have to put these tiny boxes, instrument the entire bridge. Where will you put the boxes? Which data you will collect? And the brains are somewhere over here. Okay? So there is this notion of sparsity here, not only in space, but also in number of transmissions, right?
Were you using that one of those LoRaN or something, one of those wireless outdoor protocols?
LoRa. Yeah, LoRa. And then, of course, also a lot of people say, hey, why don't you use a multi-hop network? But at least initially, our goal was to show a proof of concept. A student essentially is translating this, he's commercializing this. So why is it relevant to this workshop? In fact, the same principles we are trying to use for neuromorphic design as well. So this hypothesis we have been working on for like few years. The idea here is that a brain, as in brain in quotes, we also think we can think of it as a quasi-self-powered system. Okay, why? And this is where I will leverage some of the previous presentations that have gone on over here. What we know is that brain, at least what the different dynamics that you observe in neurobiology, it spans multiple scales. So Professor Barani, when he talked about insect olfaction, he talked about all these different dynamics, stimulus-induced dynamics, short-scale dynamics, and long-scale dynamics. So we know that there are these dynamics that exist ranging from microsecond to millisecond. So that could arise from excitation inhibition. Again, the mechanisms are not clear, or it could be like in the order of seconds. Okay, these are attractor dynamics. And then there was an excellent talk yesterday by Professor Dirisha. She was talking about memory consolidation. This can go from hours, days, all the way to years, right? So this is something that nobody disputes about. Right? The question is, in this paradigm of this quasi-self-powered type of architecture, the idea is that because you are optimizing for energy or power constraints, these dynamics are emergent, okay, as you are minimizing the energy, and it naturally does computing, memory, learning, and communications. So you are not handcrafting them. You are not doing a bottom-up design, but more of a top-down design. Okay? Quantum systems are designed the same way. You start with the system Hamiltonian, and then all the dynamics emerge because of collective phenomena. So the simplest paradigm that can be here is, and I'm just showing this as, there are essentially three blobs, and this could be controversial, but at least, if we can make it work and we can show that there are all these three different scales, time scales, which does something useful, then at least we know that engineering-wise it works reasonably well. In this model, synapses are the main workhorse. That's why, the title of the talk, Synaptic Intelligence. And the neurons and dendrites, astrocytes, whatever you want to add, they are effectively acting as energy harvesters. Their goal is to take the energy, metabolic energy or whatever, and try to drive the synapses. Okay? So if you need a spike because you need to change the state of the synapse, yes, spike has to be generated. Otherwise, as we saw in Professor Raman's talk, there are neurons that don't spike. Okay? So subthreshold oscillations have a role. All those analog dynamics can also be modeled within this framework. So the idea here is that you kind of have to optimize all these three factors together in the context of energy dissipation or energy efficiency. Okay. So the takeaway in today's talk, the first, I'm going to show that static synapses, or I would say static memory, are not optimal for energy efficient training and learning. This is typically what's used now, at least in physical synapses. I will show proposed learning in memory is a possible solution. And then the third part, if hopefully I might have to speed through this, I will show that a physics of quantum tunneling gives you the optimal dynamics. Okay, so before I start going to the nitty-gritty details of the talk, let me motivate this. And I think there was another presentation which showed what was the energy footprint for training and brain scale AI. I will present that data in a slightly different way. So this data is already publicly available. What I'm plotting here are some standard machine learning models in terms of the number of parameters, trainable parameters. And on the y-axis is the number of flops that has been reported to train some of these models. Okay? And the idea here is that I want to get an empirical estimate, what would it take to train a brain scale system. Okay. So first thing, there are a lot of interesting data points over here. So the red dots are the ones that are reported by academia. The blue dots are the ones which have been reported by industry. What you can see is that as the number of parameters have increased, everything is done in industry. Academia, they don't have resources to even train a large scale AI. So that's one thing. That tells you that probably we need to do something about this. Second, and all the transformer models lie over here. So DALI, GPT-3, GPT-4. So the first thing you will observe here, the trend that you observe, for reasonably small number of parameters, the number of flops or the operation that you need for training is quadratic. And which makes sense because for training, you have to do pairwise parameter comparison. Okay, if you need to do a full scale training, right? But the newer models, the trend is approximately linear, okay, which means that you are just looking at one pass through the data. And that, is it sufficient for training? Nobody knows, but at least you don't have the resources to do a quadratic scaling. Okay? So at least these two trends show up. Okay? So what we are going to do is that we are going to extrapolate this and say, okay, look, approximately brain has 10 to the power of 15 synapses. And then I will use the more optimistic trend the linear one, and say that, okay, if at this number of parameters, it would require about 10 to the power of 27. You might argue, hey, can it become logarithmic? I don't know. Okay? But at least you need one pass through all the parameters. You have to touch at least one parameter once. If you have to do that, it has to be a linear. Okay? So this is approximately the number of flop that you need to train a brain scale system. So I will throw some numbers related to this, and these are, I will justify the first one, but if please, for now, assume that, okay, if you have a 1 TOPS per watt system, so most FPGA work in gigaops per watt, this means that you would at least dissipate 1 petajoules, right? That's about 1 million gallons of gasoline. And this is for only one training pass, okay? If you have to do multiple passes of training, you have to multiply by that number. So that's one of the reasons, like the next GPT, one of the challenges is, okay, how do you actually tweak some of the parameters and retrain some of the systems? So if I take another number, so this is 100 TOPS per millimeter square, this number came from compute in memory architectures. This is kind of the best possible compute in memory architectures, assuming no communication bottleneck, nothing else. If you use the single chip with this density, it will take this many number of years to get to this number of flop. If I use a Cerebras type of system, a wafer scale, with this optimistic compute density, it will still take me 8 years. Okay? So this is just to highlight the scale of the problem. Okay, why, what we are trying to address over here. Yes. Yes.
Are you assuming fixed point or floating point TOPS?
So I will say that this number is 10 bits training. Okay. So this is for training, and that's one of the problems, that you need a little bit higher precision than inference.
Exactly, that's optimistic.
Yeah, that's very. So these are all very optimistic numbers. These will be worse than some of these things.
Could you explain your reasoning about this quadratic scaling?
So I'm not.
I don't understand this reasoning where you have to do pairwise comparison.
So it's
you're doing stochastic gradient descent. So how does that relate to this comparison or quadratic?
Yeah. So at least in this region.
Not that region, the other region.
Yeah. So in this case, because you have the computational resources to do a full regularization, and you can actually do Hessian type of an optimization too. So here because the number of parameters are less, so you can throw in more computational resources. Here you probably can't do any of those things. So you have to rely on online methods. That's my understanding, so please.
So the trade-off is that it trains slower.
Yes, but maybe if we are able to do this type of a training here, maybe it will get you a better solution. We don't know. Okay, so where are the bottlenecks? And everyone agrees to this in hardware community. Computing is cheap. The bottleneck comes from memory and interconnect, right? So what are those bottlenecks? So first of all, there is this memory wall. Everyone knows this in hardware community. This shows up because you have to retrieve data, weights from memory, and if you have to do it repeatedly, there is an energy cost because of the interconnect, and also because you have to access the memory repeatedly. Okay. Second, and so in literature, people have proposed the solution, compute in memory architecture. In fact, this concept came from neuromorphic community. But we kind of dropped the ball, and then different communities took it. And so just as a side note, but there are other bottlenecks as well, especially when you're training a system. So update wall, where does this come from? Effectively, when you're training, you need a higher precision of weights. You cannot go down to 4 bits as a lot of inference engines can. Sometimes even for scientific applications, you have to go to 32 bits. Okay? And then memory writes take more energy than memory reads. Okay? So there is an update wall. And then this third bottleneck is this consolidation wall. And that shows up because you have only finite memory that you can store in proximity to the compute cell or inside the compute cells. Most of the time, you have to swap in data from a short-term storage and a long-term storage, right? Cache hierarchy. And this itself is going to be a big bottleneck. Okay? So this is what we call memory consolidation wall. Okay. So what we have been proposing is that, okay, we can have a solution, at least a theoretical solution, and I'm going to show some practical directions that we have been going, is using learning in memory, you might be able to address these two bottlenecks. Okay, so what is learning in memory? So I'm going to go a little bit slow. So here the assumption is that when you're training any AI system, your weights are stored in some physical location, or it's, in this case it could be a RAM or something else, and you're minimizing some loss function. Okay? And then the hope is that during the training, as you are updating those weights or the memory locations or the values, the loss function goes down up to a certain point. So it shouldn't go down to 0, but I'm just showing this over here. At that point, you stop the training and then you enter into the inference phase. Right? So here, for a very simple, quadratic type of a thing, you start with this initial weight, high dimensional, and then you follow a trajectory. You get to some local minima, or in quadratic, it's a global minima. So I'm going to abstract both the memory and interconnect using this very simple, bistable potential. Okay? And this is a standard method that is used in modeling memory. Here, what it means is that this is the weight at any instant of time n-1, and this is the weight at the next instant of time. There has to be an energy barrier that has to separate these two states. To get an understanding of what a state is, think of this one state, this dot is a state of a Rubik's Cube. So you can think of the weights as a configuration of a Rubik's Cube. And as you are changing the state, which you're updating the memory, you're effectively kind of manipulating the Rubik's Cube, right? Okay, and so when you make a transition from this to this, what you want to make sure is that once you have manipulated the Rubik's Cube, it doesn't come back. So you need to have a certain amount of energy barrier that hinders that state to come back. Okay? So most memory systems are designed to make sure that this energy barrier is high enough so that your memory retention is as high as possible, at least to a certain reliability, few hundreds of KTs. Right? And our goal is to get to this final solution based on these memory updates. The second assumption that is typically made, and this is practical, is that these are not reversible. So once you dissipate the energy in making this trace transition, you cannot recover it back. There are energy recovery based methods, reversible techniques. So you can think of this Rubik's Cube, which is spring loaded. You manipulate it and then you let it go, and you can recover the energy back. Most practical systems, it's very difficult to do energy recovery. Okay? So if we go with this simple model and we say that, okay, where is the energy being dissipated? It's mainly this E0, this barrier height that you have to at least elevate the state and then dissipate it out. In most practical systems, this would be in the order of 10 to the power. This is about 100 femtojoules. This is pretty optimistic. It doesn't take into account interconnect and other stuff, right? So it's just the memory update. Yes?
What is the space form?
10
to the minus 7. Is
Yeah.
it temperature or what?
So this is 10 to the power of, joules per bit. So for one state change, we are saying that, okay, there is about 100 femtojoules of energy that you have to put in.
Why not 10 to minus 6?
Okay, so there are two things. First, so this barrier height depends, that's the number of energy. Okay, that's the amount that you need. The second reason comes from why you need to have is, so if you think about this, what constitutes a state? In a practical system, this state constitutes of tons of electrons. Okay, many electrons that are pushed to this energy level and then they are pushed down this well, right? So why can't you do operations with one electron? The answer is that because you have to measure the state to do computation. So there is a measurement limit. Also, there is this energy barrier limit. So when you combine the two, you end up with this number, a practical number. So these are like, so memristors typically get to about 1 picojoules per bit. Okay, so these are from a practical device numbers. Right? Now, this is an order of magnitude higher than Landauer number, which is about 10 to the power of minus 19. Okay, so, and there's a reason why.
What about an SRAM bit? State-of-the-art SRAM bit. How much energy is that to store an SRAM bit?
Yeah, so SRAM would be much lower than this. I agree. So this is 100 femtojoules per bit, but again, I'm still taking an optimistic number here. You can go down to close to 1 femtojoules per bit for SRAM. Even I have seen autojoules number reported for SRAM as well. Okay, so if I take this, okay, this number, and I assume 10 bits precision of update, this will give me about 1 petajoule. So that's where that number came from. But this is a very optimistic number. Okay, so what is learning in memory? Again, the same curve. But now what we are saying is that instead of keeping the energy barrier constant for the memory, you adapt the energy barrier. Okay? So in the initial phase of the training over here, we will keep the barrier low. Okay? So which means that we will sacrifice the retention of the memory. Okay? But as the training ends, you start increasing the weight retention. Okay? And why is it okay? Because there is enough redundancy built in the learning process to compensate for any errors that happen initially. Okay? So the reason why most of the time you are dissipating energy in this mechanism is that somebody who writes software says that, okay, your gradient updates has to follow this specific trajectory. And as a hardware engineer, we have to follow the trajectory. We don't have any flexibility or in terms of entropy of this path. We have to follow this specific path. But if we relax that constraint over here, we allow the learning algorithm itself to correct for some of those errors. So which means that initially we are dissipating less energy to make this update. But then later on, if the updates happen in this stage, we are dissipating more energy. But the hope is that at this stage, the number of updates itself is very low, because the machine is getting trained, or the model is getting trained. So that's the idea of this learning in memory. But what are the implications of this? Is because initially our goal was to follow this trajectory, but because we have initially the barrier to be low, there are many other paths it can follow now, right? But the goal of this is that you have to inject some external energy to correct this path, so that it can guide it to the final solution. So you can think of it in the Rubik's Cube. You dismantle the Rubik's Cube, and then you let the system arrange it. Of course, you can't completely dismantle it, but up to a certain degree. So again, this is just a visualization over here. So the energy dissipation in this model would be the energy required to modulate the barrier, and then the second is the energy to do this gradient correction. And this is the trick that is used in space launch all the time, because you can use gravity as a way to correct the trajectory of many of the spaceships. So again, this is a trick that has been used in other systems as well. Okay, so what are the key components in this learning in memory? Again, going back to this picture. So as I said, synapses, neurons, and the neurons are acting as energy harvesters. We have this synaptic dynamics where we are modulating the barrier up and down. So now what we need to do is that if this barrier is initially modulated such that first based on some dynamics, the state changes quickly in the initial phase, and then you start applying the brakes so that you can stop the solution at the right location. Okay, so by changing the barrier, that's what you want from the synaptic dynamics. From the neuron side, what you want to shape this energy contour such that it can drive the synapses in the right direction. Okay, so the neurons have to kind of modulate this energy barrier, and the hope is that this physical energy is going to match your loss function that you want to minimize. So here the physics and the algorithmic part match very well. So the challenge, of course, is how do you adapt this energy barrier such that it can match the dynamics of the loss function. So of course there is some pre-knowledge that has to go into here. Any questions before I move? Okay. So the neuromorphic aspect of LIM, synapses, the retention and plasticity, there is a one-to-one relationship between the two. Yesterday there was an excellent talk on metaplasticity. This has been observed that the synapses, they change the plasticity based on importance, age, and usage. In fact, there was a great tutorial in the afternoon yesterday where I think Anurag, he gave us like an introductory idea of like how you can use metaplasticity for memory consolidation. And this is typically what's assumed, that even from a neuromorphic point of view, there is this working memory and long-term memory. The memory in hippocampus they are updated faster, so because they are scratch memory. The ones which are in the neocortex are the ones which have high retention. They are less frequently updated at night. Again, that's the hypothesis. So from an engineering point of view, it means that what we are looking at is a flat memory system. Okay? This one, the scratch memory, are like the registers and the cache that are updated constantly. And then this one are like the SSDs, or on the hierarchy over here. So which means that the energy barrier on this side is pretty low, on the energy barrier over here for the SSDs are pretty high, right? And then we are not sure what the coupling is. So the coupling here is where the secret sauce lies. Okay, so there are 3 questions that you can ask about this framework. And the rest of the talk, I'm going to essentially show results from these 3 papers. I can post these 3 papers if you want to delve into a little more details. So what are the optimal synaptic devices? Energy efficiency limit, this is an ongoing work. This is a collaboration with Gert Koenbergs. And then the third part is now how we can use some of these synapses in an actual neuromorphic architecture. So we have some preliminary results using shallow networks. We still have some challenges, a lot of challenges in scaling it to deep networks. Okay, so these are 2 work in progress. So what are the optimal metaplastic synaptic devices? So again, I will give a neuromorphic perspective of what optimal synapses are. There was an excellent talk yesterday afternoon by Professor Rishikesh, who showed that in biology, neurobiology, there are lots of these degeneracies. Okay? So there are many different paths that can achieve the same function. Biology does it because it tries to achieve so-called robustness. If one path goes away, at least there is another path that can give you the same functionality. Synapses are also a highly complex dynamical system in itself. Okay? And there are different time constancies for different cascading pathways. And there is a consistent model, and there is one famous model called a cascade model, which argues that, look, the purpose of all these different pathways is to achieve some optimality in terms of the characteristics of the synapse. So these nitty-gritty details of what these pathways doesn't matter. It's the collective behavior of these pathways that are more important. Okay? So this is by Stefano Fuzzi. And then the objective of thinking about an optimal synapse, it's one that can maximize the capacity of a memory. Okay? So this is a very nebulous term. What does memory capacity mean? There is a standard benchmark that we can use, and I'm going to just talk about it a little bit. This benchmark is called a random pattern test, and the reason why people use this to measure memory capacity is because it's analytically tractable. Okay? You can talk about bounds and things like that. So think about that you have a favorite childhood memory, okay? And as you grow up, it gets corrupted by lots of different things, okay? And so the question here is that, so these are all different random noise. The assumption in this task is that these noise, these different interferences are uncorrelated with the original image and also with respect to each other. So the question here is that you ask, is this image still stored in this corrupted memory? Right? So it's a very simple task. And so if you add some math to it, so if x1 are all these different uncorrelated zero mean parameters, at the end you have a total memory, which is just a superposition of all these different inputs, random inputs. Right? So you can define a signal strength, and you can define the variance, which is the noise, okay, across an ensemble, and you can say that, okay, this pattern is present later on if the signal to noise ratio is greater than 1. Okay, the signal is equal to the noise level. That's the standard task that's typically assumed. But the challenge is that if you keep adding this variable, even though they are uncorrelated with respect to each other, they have finite variance, this weight is going to keep blowing up because the variances add up in square root, so this will keep blowing up. These are so in this case, so if I just keep it as it is, it can store up to n patterns. Okay, why? I can think of every synapse in this case storing one specific, so it's an eigenvector. Each eigenvector you're storing, so if this is an n by n type of an image, you actually can store n directions. Okay, so this is you can't do better than that. So the challenge in this model is that the variances add up, so this system, this synapses become unbounded. In practice, the synapses are always bounded. So what Stefano and his students, Marcus Benna, they did is that they asked this question, okay, there has to be some memory decay term. So you can't keep adding this term all the time. So you have to add some decay. What is the optimal value of this decay that will give you the best capacity? Okay, if this is unbounded, we know that the number, you can store only n patterns. Can you find out what is the value of the rate such that it can do at least as good as n? So they came up with this cascade model, and they said that, okay, if this memory decay follows as 1 over square root t, then it gives you at least a capacity you can store n over log n. Maybe not n, which is the best possible, but n over log n. So and they showed optimality using this random pattern task. Okay. Questions? So we are going to kind of use this result to design a device that can generate these characteristics.
Okay.
Yes?
So I have a question, because this is directly relevant to the Hopfield network, right?
You can use it in the framework of Hopfield network.
But it's relevant to that because the capacity of the original Hopfield network was order n also.
Yes. Yes.
Which is very low capacity, right?
Yes.
Because you basically can only store the number of vectors you can store is just proportional to the number of neurons, not the number of weights.
Yeah. So here.
Just the number. Yeah.
So here it's kind of the same, because here each dot is a synapse. There each dot is a neuron.
Yeah. But now the dense associative memory broke that. You're going to talk about that?
No. So dense associative memory is a nonlinear system. So yeah.
Which is fine. I mean, what's wrong with being nonlinear?
No. So there are lots of challenges. So yeah, I'm not going to talk about dense associative memory. Yeah. Yeah. Okay, so we are going to use this result to design our optimal synapse. So the question is, how do we do it with a practical substrate? So the next criteria that you want from a synapse is they have to be relatively small, because you want to pack as many devices into a single substrate, and you want this to be simple. So I will take a very simple abstraction of a dynamical system, okay, and I've used this as a water clock, sand clock. And it has to follow a characteristic that looks like this. As the sand falls, you are measuring the state as a total number of amounts of sand over here, and it has to follow some first order differential equation. Okay, so I haven't quantified what this rate is, J, over here. So
What's that sand?
So here I haven't, it's some quantity. It could be water, electrons. We'll see it will become electrons. It could be a memristor where the filaments, these are multiple states of a filament. So I haven't quantified. I'm keeping it general right now. And then I take another of these. These are, one, this could act as a reference, and this could be another synapse or of these devices. And initially I align them, time align them. So over here they are together. And then I perturb this device. Because I'm perturbing it in this fast transition state, it deviates from each other, but then it starts resynchronizing again. And again, this is a property of the dynamical system by itself, if you choose it correctly. So they will resynchronize itself. So here we can think of it like this is like a fast adaptation mode, low retention mode, or more plastic mode. If you do this later on, it takes longer time to resynchronize. If you do it at a later stage, it will take long time for these two systems to resynchronize. So here it constitutes a slow adaptation and a less plastic state. So using this simple dynamical system model, I haven't defined what J is. Okay, I can implement this metaplastic synapse. Okay. So now what we will do, again, as most circuit designers do, we will make this differential, and I will apply this signal also differentially, an external signal, perturbation. Okay, so differential mode, common mode. Okay, so this is also most of the circuit designers know. And then I will make the assumption that the common mode is going to be much larger than the differential mode. For some of the devices that we will look at, this is actually going to be valid. And then if I plug this expression into both of these dynamical system model, and again, I would refer you to the paper for the math, what turns out to be is that you have this one differential equation that is determining how the differential weight is changing, and then there is another factor which is telling you how the common mode is changing. You see that the common mode doesn't have the differential component, but the differential equation has this common mode constant in the decay rate. So this is the first order term, and then this is the decay term, and this is your WD. Okay? And this part is your weight. This part we will see is going to be the usage, but the leakage rate over here, okay, is what will determine the barrier. Okay? So lower the barrier, the lower the leakage, the higher the leakage rate is going to be. And this is controlled by another dynamical system that we can control by this parameter WC. Okay, so our neural network or whatever learning model that you will not have just one parameter, but will have two parameters simultaneously. So a differential part and a common mode part. Okay. So now what we want to do is that we want to connect this decay to this optimal decay that has already been reported. This is the square root of t. Okay. So how do we connect this to this? Another result from computational neuroscience. This came from the cascade model by Stefano Fuzzi. Okay. And then there was a recent paper, it's not recent anymore, from the elastic weight, this is from Google DeepMind, Kirkpatrick. They showed that this dynamical, so you can think of this as an FIR filter. There is an equivalent of an IIR filter, which is over here, but this coefficient becomes 1 over t instead of square root of t. Okay. So now, because our synapses are in this form, we can directly connect this 1 over t to the thing that we need to determine the decay parameter. And just to refer to the previous talk, yesterday's talk, this is also connected to a Fisher information matrix, but for uncorrelated patterns. So there are lots of details that are associated with this result. Okay, so back to this, our model. So we want to connect this decay rate to this 1 over t, okay, which means that we have to make sure that what type of this function satisfies this 1 over t. So this is giving you a class of optimal synapses. Again, I haven't defined what the decay function is, just j is, and that is what I need to find out. Okay, so now I will start putting some of the physics behind what this clock is. Okay, so simplest way to implement a dynamical system is a capacitor that leaks, okay, and I haven't again defined what this leakage current is. The criteria that we need is that this leakage has to span over hours and years, because if you're doing a consolidation and learning which spans over a long time, this time constant has to be pretty large. Right? So how do we do that? So these are the two criteria that we have. This is our leakage current, but it has to satisfy this criteria. Okay? Several options. Okay? But the challenge here is that if I have a capacitor of 1 picofarad, again this is pretty large and if I look at a 1 volt change over 1 year period, it means that I have to deal with currents which are about 32 zeptoamperes, or 1 electron every 5 seconds. Right? So if I take a standard leakage element like a resistor, which is current is directly proportional to the voltage, it will give me an exponential decay. First of all, it's fast. And this decay is fast, but it also doesn't satisfy this criteria. So if I take the derivative of this and all this, it doesn't satisfy this criteria. Reverse leakage gives you minus t decay, linear decay, but it also doesn't satisfy this criteria. Translinear elements, which is yes, it satisfies this criteria. So this is fine. Okay. So on the log scale, you will have this plot. So this actually can be used to implement an optimal synapse, but this is also fast decay. We want even a slower decay than this, okay, than log. How can we do that? It turns out that if you use the physics of Fowler-Nordheim tunneling, whose current equation is given by this, so again this is a standard term, and you go through the math, you will get a 1 over log. Okay? And this 1 over log does satisfy this. Plus, it also have a much longer time constant than the translinear element. Okay, and so this is the one that we are going to use for our Synapse implementation. Any questions?
Yes.
Yes.
Why is it the ratio of the acceleration to the velocity? What's the intuition about that? Is it the second derivative of the weight with respect to time?
Yes. So second derivative.
By the first derivative.
Yes.
of the weight?
So there are two. So first is the math. So if you go through the math, it will naturally fall out of it. So that's one. But the intuition is that this actually has a very similar representation as a Fisher matrix. So Fisher matrix has second order derivative and the first order derivative.
Doesn't help me.
Yeah. But that's what it's essentially telling you, that the acceleration has to decay with the ratio of the linear decay has to be 1/t. But yeah, the math directly gives you. And we are trying to figure out what is the intuitive reasoning behind it. But the math here, we are only relying on the first order differential equation.
But what's t? T is just time, right?
T is just time.
Decay like 1/time.
Yes.
This thing should decay like 1/time.
As 1/time.
This ratio.
Yes, it's a ratio. And again, right now I haven't put any units over here. So this J also is units. So once you add units, this will, a lot of things will cancel out. Yeah. So I will show an implementation of this, and probably that might clarify some of the doubts. Anything else? Yes, sorry.
Can you say again, how did you find this time constant that is only achieved through the quantum tunneling? And I mean, that depends on the speed of the training. And
yes. So here everything is continuous time, right? Meaning here I'm showing it's a good, but you can always shut down the device as well. So the way we actually implement this is that we try to do this in discrete time. But yeah, meaning here all the derivations are in continuous time, but
you cannot stop the leakage.
no, so that's where there is some element of control. If with floating gates, you would be able to do a lot of things. But yeah, I agree. Ideally, you want your training data to come continuously, in an online manner. But in practice, it's very difficult to do that. So what we do is that we kind of shut this down and turn this on, which actually dissipates a little bit more power. But ideally, you want the data to come on continuously, your inputs. I know, Jennifer, you had. Okay. So I generally don't show this data, but because we have lots of folks from circuits community, I'm showing some of the characteristics of the Fowler-Neuheim device. And I want to highlight few points over here. So here there are many different devices that we made. Okay, different form factors, different tunneling junctions, cross-sectional area, different temperatures. We initialize them to some random point, as close to each other as possible. So here, why it's a high voltage? Because for Fowler-Neuheim tunneling, you need a high enough voltage. What you see is that there is an initial part, which is this transient region, and then after that, it reaches this so-called equilibrium region where the decay rates are practically equal to each other. Okay, irrespective of the device form factor, independent of irrespective of the temperature. Okay, so it tells you that this phenomena is very robust. So as long as I can calibrate for this initial decay, if I start from this point, these lines, or I would say this decay, would be very well synchronized with respect to each other. And this is very important for synapses because it helps us to do modeling accurately. Okay. So here is an example. So yes.
For the earlier case, all these, what you are plotting is the floating gate voltage.
This is the floating gate voltage.
With
Decay.
different capacitors, you are still getting the same decay rate.
Yeah, so initially the decay rates are different. But then they reach a region where the decay rates become approximately equal to each other. And there is a very nice physics reason from device physics why that is the case. Okay. Yeah. So our original intent for making this device was something else before we saw that it actually has an application for synapses. We were using this as clocks. Clocks in systems, in self-powered systems which didn't have any power, so like an RFID. Right? So if I take this device, one device, and I give one to Toby, he goes to Zurich, this, we can show that both the device will remain synchronized with respect to each other as long as the temperature has been maintained to be the same. Right? And that feature you can use for many different things. So we have shown previously about a few years ago that you can use it for key exchange. So because each of these dynamics is very unique, you can use this to couple it to a random number generator. So your random number generator and my random number generator can be synchronized with respect to each other. Right?
But why does this tunneling depend on temperature? Normally tunneling doesn't depend on temperature, right?
It does. So that's so you see that in the initial case it does depend on temperature. But what happens is that it reaches an equilibrium where the temperature variation, so they compensate. There's a self-compensation mechanism here. Okay. So here we see that the mismatch and synchronization is pretty good for this device. The next question is how long can this dynamics last? So remember a PhD lasts for about 5 years. So this experiment, we couldn't have run it like a PhD student looking at how long can this last. So what we did is that we subdivided this into several regions. We took an initial part where we let it decay. Then we reinitialize the device. We let it decay for a little bit of time, few weeks. And then we reinitialize it and let it decay for a few weeks. And then we see that there is one curve that fits through all of them. So it's just giving an extrapolated result that indeed this is one decay that is explaining the dynamics of this. So what we know that it can last for at least 1.5 years. It can go even better, higher than that. And it also tells you the validity of this 1 over log T model. The challenge is that at this decay rate, we are talking about 1 electron per minute. Okay? So it's highly quantized. So it means that your synapses are becoming probabilistic at this node. So you have to start dealing with more of a probabilistic updates rather than deterministic updates.
So,
yes?
So if Toby takes it to Zurich and he goes in the airplane and gets more radiation, does that start impacting?
Yeah, absolutely. It's floating gates, absolutely. So
it wouldn't remain synchronized without
it won't be. You have to shield it. Yeah. So even like if you change the temperature, it will desynchronize too. Okay. So here are some examples of measurements where we show that indeed, that if you perturb the system at different time instance, you can get different retention rates. So just like what we had anticipated in the cartoon that I showed before. Here is an example measurement from metaplasticity. So if you take a single synapse, you update it with different potentiation and depression pulses. Initially, the updates are fast. So here we are applying a large pulse. So we are intentionally trying to show this result. This change in voltage, I would be close to like hundreds of microvolts, but we are applying a large enough pulse over here. But you see that initially the voltage change, the weight change is high, and then it's becoming more rigid over time. The beauty of this device is that it only takes 1 femtojoule per update because it's floating gate. So you just need to modulate the charge a little bit, and it can change change its properties. Okay, and here is an example where we used it for the random pattern test. Here it shows that the weights remain bounded, so it doesn't go all the way to infinity. And these are Monte Carlo results, both measured and simulated. They match very well, again, because the device mismatch is minimal, I would say. And they match the analytic and simulated characteristics. So it verifies that it actually indeed follows 1 over square root T. The key thing is that the simulation matched measured responses. So it means that we can do a lot of our studies in software using this model. And we can have a fairly good confidence that it will work if we do a one-to-one mapping on hardware. Yes?
I thought that the matching of these floating gate devices was terrible. It sucked.
Yes, so Jennifer is here. So I will be very careful in making this comment. So I agree. So, but in this case, if you let it self-calibrate, in this region the matching is pretty robust.
Okay.
So the calibration phase is that you have to let this memory decay first for a little bit of time.
Okay.
And then you have to zero out this offset.
You store that offset somehow.
Or you look at the change. So for training, it will not matter. Okay. Yeah, and so we ran the standard consolidation result, which is, I think, yesterday somebody gave a tutorial. Split MNIST, I'm just going to go through this quickly. It's not the state of the art because this was done a long time back now. But what I want to highlight is this. So when we compared it with an RRAM, a memristor based, and we use this metaplasticity based training, we see indeed a 10x improvement. Again, here what we are doing is that we are taking the gradient, somebody else is calculating the gradient, and using the gradient we are updating the memory. So ideally we want this learning to be local. Okay? But even by taking the gradient and computing it externally and then updating the memory, we get a 10x improvement. Yeah. Okay. So the last, let me see, how much time do I have?
About 10 minutes.
It's done, yeah. Okay, so the last part I'm just going to talk about, briefly mention, like how we are trying to use, embed this synapses in a neuromorphic architecture. Again, 2 papers, if you're interested, it has some details over here, but it doesn't have those metaplastic synapse. The first paper is telling you using energy minimization, how does it naturally produce synapse, like spikes, bursts, and other things. The second paper tells you how, if you let a system evolve, how does, using local learning rules, the firing rates become more and more sparse. So here is an example of the second paper. The idea here is that you use the energy, the physical actual energy, as a regularizer, right? So if you constrain a system with respect to energy, it will try to choose the one more efficient path. That's the whole idea, right? So in system over here, so we have a bunch of coupled neurons, and here the green dots are like the firing patterns, firing rates, so they are all kind of look clustered together. So you can think of this as a reservoir, right? So we ran this network for an olfaction task. So if I take these features, these different reservoir features, and then we train a classifier, and a lot of people have done this experiment before. Indeed, you get these well-separated trajectories that differentiate between different orders. Okay, that's not the point over here. But then we let the system adapt over time, again with different the metaplastic rules. As you proceed over a longer time scale, the trajectories over here shrink, okay, which means that it's dissipating less energy, and I will show why. But when we train the classifier, the discrimination remains unchanged. So you are using less spikes than before over here, but it's still performing as well as the original network. So this is another way of thinking about learning. If you become more proficient in a given task, you're dissipating less energy. That means that you're learning a task better. Okay? And so when you look at the eigenspectrum in both of these domains, before training, the eigenspectrum looked like this. So it means that there was more energy in very few patterns over there. But then once the network sparsified itself, the eigenspectrum looked like this, which means that it has learned to use more sparser codes. Okay? I don't know if we can claim it's neuromorphic or not. At least we know that it has implications from energy efficiency, and you can clearly see that the firing pattern is much less over here than this. Okay. So with that, I will put this picture again. This is the approach that we are taking. We are assuming that the brain is a quasi self-powered system where most of the work is being done by the synapses, and what the neurons and all the other stuff is doing is they're trying to find an efficient way to channel energy to drive these synapses to do a specific work. And our hope is that some of these multi-scale dynamics naturally emerge from the energy minimization process. Okay? And that also is related to computing, memory, learning, and communication. So we are not handcrafting a communication. Hey, this neuron needs to communicate with this neuron, and hence you have to design a route for this. If the neuron needs to communicate with this neuron because the learning or the energy minimization requires it to do it, it will find a path to do it. Okay, that's the approach we are taking. So with that, I will take any questions.